closest to the sun and shrouded in searing heat, Mercury might seem like the least likely place to unlock the secrets of planetary formation. A world of blistering days and freezing nights, cratered like the moon and almost airless, Mercury is often overlooked, small, mysterious, and hard to study. Yet beneath its scorched surface, Mercury hides a riddle, one that has puzzled scientists for decades. A strange wobble in its rotation, subtle but unmistakable, suggests that something unusual is happening deep inside the planet. This wobble, known as libration, isn't just a curiosity. It's a clue, one that could reveal how Mercury formed, how it evolved, and what it tells us about the origins of planets across the solar system, including our own Earth. So how does Mercury's odd spin shed light on the ancient mechanics of planetary birth? Let's take a closer look at this enigmatic world and the surprising insights hidden in its motion. At first glance, Mercury's rotation seems straightforward. It spins slowly, taking 59 Earth days to complete one rotation, and orbits the Sun every 88 days. But this is no ordinary spin-orbit relationship. Mercury is locked in a 3:2 spin-orbit resonance. That means for every 3 rotations on its axis, it completes 2 full orbits around the Sun. This rare configuration creates a bizarre day-night cycle and unusual patterns of sunlight across its surface. But things get stranger. In the early 2000s, radar observations revealed that Mercury doesn't rotate with perfect smoothness. Instead, it wobbles slightly as it spins, a phenomenon called longitudinal libration. This wobble is tiny, just a few arcseconds, but detectable from Earth with high-precision instruments. And it has massive implications, because for Mercury to wobble the way it does, part of it must be moving independently of the crust. In other words, the planet's core isn't solid. It's at least partially molten, something no one expected from such a small, ancient world. Mercury is the smallest planet in the solar system, just slightly larger than Earth's moon. Given its size, scientists long assumed that its core would have cooled and solidified billions of years ago. But the discovery of its rotational wobble suggested otherwise. The wobble indicated that Mercury's outer shell, its mantle and crust, moves slightly independently of its core. That would only be possible if a liquid layer exists between them. In other words, Mercury still has a molten metallic core, at least in part. This revelation shook our understanding of planetary evolution. How could such a small body retain enough internal heat to keep its core partially liquid? One clue lies in Mercury's enormous iron core, which makes up over 85% of its radius. For comparison, Earth's core makes up only about 55%. Mercury has the highest metal-to-rock ratio of any planet, and no one is entirely sure why. Some theories suggest it lost much of its rocky mantle in a giant impact, or that it formed in a region of the solar nebula unusually rich in iron. Either way, the molten core revealed by Mercury's wobble opens a new chapter in understanding how planetary interiors evolve, especially for small, dense planets. But how do scientists detect something so subtle as a planetary wobble, especially from over 90 million kilometers away? The answer lies in radar science and Doppler measurements. Using facilities like the Arecibo Observatory and NASA's Goldstone Deep Space Communications Complex, scientists bounced radar signals off Mercury's surface. By measuring the time delay and frequency shift in the returning signal, they could track the planet's rotation with extraordinary precision. These observations revealed periodic variations, tiny deviations in Mercury's rotational speed and angle. These librations matched models that predicted a decoupling between the crust and core, just as would happen if a liquid layer existed. Additional data from NASA's Messenger mission, which orbited Mercury from 2011 to 2015, further confirmed the planet's internal structure. Gravity field measurements, topographic mapping, and magnetic field analysis all pointed to a molten outer core and perhaps even a solid inner core like Earth's. Mercury's wobble isn't just a physical motion. It's a diagnostic tool revealing what lies deep beneath the surface, a kind of planetary stethoscope for one of the most elusive worlds in the solar system. So what does all this tell us about how planets form? Mercury challenges almost every assumption. It's too small to have a molten core. It's too dense for its size. It has a magnetic field, albeit weak, something that requires a moving liquid metal core like Earth's. And its surface is ancient and heavily cratered, suggesting it's geologically inactive. One theory proposes that Mercury began as a larger body with a thicker rocky mantle. Then, in the chaotic early solar system, it was struck by a giant impact, blasting away much of its outer layers and leaving behind an iron-rich remnant. This would explain its massive core and thin crust. Another possibility is that Mercury formed closer to the Sun than it is now, in a region where lighter elements were scarce and metallic materials were more abundant. Either way, Mercury's strange rotation and internal structure provide a missing piece in the planetary puzzle. It helps us understand how diverse planets can be, even in the same solar system, and what kinds of worlds might be waiting in others. By studying Mercury, we're not just learning about one planet. We're testing our theories of planetary accretion, differentiation, and thermal evolution, ideas that apply to every rocky planet we've ever found. Despite its proximity to the Sun, Mercury remains one of the least explored planets. But that's changing. In 2018, the Bepi-Colombo mission, a joint effort between ESA and JAXA, launched toward Mercury. It's currently en route and expected to enter orbit around the planet in 2025. Once there, it will deploy 2 spacecraft to study Mercury's surface, magnetic field, and internal structure in greater detail than ever before. One of Bepi-Colombo's key goals: to further investigate the strange wobble and use it to build a more complete model of Mercury's inner layers. Could there be a liquid outer core and a solid inner core, just like Earth? Could this help explain how magnetic fields form in small planets? And could it even reveal whether other small, rocky exoplanets might be more like Mercury than Earth? With each mission, Mercury becomes less of an outlier and more of a key to understanding how planets survive, evolve, and sometimes surprise us. It's easy to overlook Mercury, the smallest planet, the closest to the Sun, a scorched rock in the shadows of giants. But beneath its cratered skin lies a story far larger than its size would suggest. Its strange wobble has exposed a hidden world, a world with a molten core, an active history, and clues to the very processes that built the planets. Mercury shows us that even the most unlikely worlds can hold the deepest truths, that small planets can have big mysteries, and that by watching a planet spin, even ever so slightly, we can glimpse the grand cosmic forces that shaped everything we know. In the end, Mercury's wobble is more than a quirk. It's a message, etched in motion, echoing through the solar system. Every planet has a story, if we know how to listen.